Okay, so now we're going to start looking at the symmetry that we have within our functions. Okay, so we have different ways we can test for symmetry. So first thing, if we look at the definition, so if we look at being symmetric with respect to the y-axis, we can substitute negative x for x in the equation, and we result in the equivalent equation. Okay. So what that means is if we plug in f of negative x, we get back our original function. Okay, and that means we're symmetric with the y-axis. Okay, if we substitute in negative y, I'm not even sure how to write that because you can't write that in function notation. So substitute negative y for y in the equation results in an equivalent equation. And then if you substitute both of them in and you get back the original, then it's symmetric across the origin. So we're going to check these. So first one, if we change negative x. So does negative x equal y squared minus 1? Can we get back our original? So if we divide by negative 1, we get x equals negative y squared plus 1, which is not our original. So our answer here is no. It's not symmetric across the y-axis. If we do negative y, so x equals negative y squared minus 1. Well, negative squared is a positive. Well, that is our original, so this is yes. Okay, so now if we check both, we have negative x equals negative y squared minus 1. We get negative x equals y squared minus 1. If we try to divide everything by negative 1, we get x equals negative y squared plus 1. So this one doesn't work. So this function, x equals y squared minus 1, is only symmetric across the x-axis. Okay, so if we look at B, we're going to do the same thing. So if we plug in negative x, we get y equals negative x cubed, and a negative cubed is still a negative. Okay, well, if we divide by a negative to try to get rid of it, we get negative y equals x cubed. So we aren't getting back our original function. So this is no. We try negative y, we get negative y equals x cubed. So let's divide by negative 1 and see if it'll go away. We get y equals negative x cubed. So that doesn't work either. So now let's try both. So we have negative y equals negative x quantity cubed, which gives us negative y equals negative x cubed. If we divide by a negative 1 on both sides, we get y equals x cubed, which is our original function, so this is a yes. Which means we're symmetric across the origin. Okay, so let's look a little bit more at that. So we have even and odd functions. So an even function is, if a graph is symmetric with respect to the x-axis, it usually fails a vertical line test. It is not the graph of a function. Okay, so it's not usually a function. However, many functions have graphs that are symmetric with respect to the y-axis or the origin. We give these functions special names. So an even function is a function whose graph is symmetric across the y-axis. Okay, the easiest way to think about this even function, think about x squared. Okay, that's 2 is an even number. And if we were to graph that, we get a parabola, which is symmetric across that y-axis. Okay, an odd function is a function whose graph is symmetric across the origin. So a way to remember this, odd origin, O and O. Okay. Another way to think about it is if we look at just x, we graph y equals x, we get a line, which is symmetric across the origin because this point, we change both signs, we get the positive side. Okay. All right, so determine whether each graph is the graph of an even function, an odd function, or a function that is neither even or odd. Okay. So all of these graphs pass our vertical line test. So if we look at A, can we draw a line of symmetry? Well, our y-axis cuts our graph in half, which means it is even. Okay. Looking at B, we don't have any line of symmetry. There is no mirror image. So this is neither. And then looking at C, we can draw a line here, which makes this odd because it's through the origin. Okay, so now looking at just our functions, one way we can calculate this is if we plug in negative x into the function and we get back our original, we get even. Okay. Odd function, f of negative x. If you plug in negative x, you get back your original, but all the signs are changed. Okay. And then if you plug in negative x and you don't get either your original or all the signs changing, then it's neither. So if we look at this first example, f of x equals x cubed minus 6x. We plug in negative x and we simplify. A negative cubed is still a negative, and a negative 6 times a negative x is positive 6x. Okay, so if we look back at our original, both of our signs changed. We could factor out a negative. We would have x cubed minus
all remaining sophomores
minus 6x, which is the same thing as writing negative f of x. Okay, so negative f of x, all of our signs changed. This means this is an odd function. And we'll talk about a shortcut here in a second. Okay, so looking at g of x, so if we plug in negative x, we get negative x to the fourth. Whoops. How about negative x to the fourth power? Minus 2 times negative x to the second power. Well, remember when we take a negative to an even exponent, it becomes positive. So we have x to the fourth minus 2x squared. Well, that's the same as what we started with. So this equals g of x, which means we have an even function. Okay, so let's take a look at this. We had an odd function on part A. Now let's look at our exponents. We have a 3 and we have a 1. Both those exponents are odd. Okay, look at B. We have 4 and 2. Both of these are even exponents. So let's use that trick for for part C. So h of x equals x squared plus 2x to the first power plus 1. So they're not all even, they're not all odd, so this is going to be neither.